Chebyshev polynomials. Now, in our last video, we talked about the Chebyshev polynomials, and we were looking at the introduction, where we did consider the expansion of the expression cosine of theta plus I sine theta to power n, this expression here, using two theorems. One theorem being the De Morphus theorem, and the other one is the binomial theorem. And from the expansion, we equated the real parts of the expansion using the two theorems, and we were able to come up with an expansion of cosine of n theta in terms of cosine of theta. This expression here, which we call equation 6, and we could also replace the sine squared theta here. The square of sine of theta, remember, we can expand using the first identity in trigonometry, cos squared theta plus sine squared theta is equals to 1. We can make the square of sine of theta the subject and write 1 minus cos squared theta. Now, it means that where we have the square of sine of theta, we can replace with 1 minus the square of cosine of theta. And so, as we saw during the last video, we could replace that, and cosine of n theta can be expressed purely in terms of cosine of theta into powers of cosine of theta, as we have in the equation 7 here. Now, we saw that n here is an integer from 1, 2, 3, and so on. And when n is 1, we get cosine of 1 theta, which is just cosine of theta. When n is 2, we could express our expression cosine of 2 theta in this form. And we want particularly to consider to set cosine of theta to be equals to some value x, so that when we write cosine of 2 theta, then we get something like from here, we get 2x squared minus 1. Similarly, when n is 3, we can substitute the values and come up with this expression here, cosine of 3 theta expressed into powers of cosine of theta. And if we replace x, or rather cosine of theta with x, we can write cosine of 3 theta is equals to 4x cubed minus 3x. So we can express cosine of n theta into powers of x as a power series in this case, where x is equals to cosine of theta. And we say when n is 4, we could also expand that. We can continue like that, n is 5, n is 6, and so on. That is what we did look at in our last lesson. And today, we want to look at the definition of a Chebyshev polynomial. Basically, the Chebyshev polynomial, which is denoted by Tn of x, T subscript n, a function of x, we define it as to be equals to cosine of n times cos inverse of x. We define it in this form. This is the Chebyshev polynomial. Sometimes we call it the Chebyshev polynomial of the first kind. And we see that if we put n here is an integer which takes values from 0 to 1, 2, 3, and so on. So that if we write something like t is 0, if we write t is 0, x, so that n is 0, Then we shall write cosine of n is 0, times cos inverse of x. 0 times cos inverse of x will give us 0. So this becomes cosine of 0. And cosine of 0 is 1. If you find cosine of 0 is 1. So Tn of 0, sorry, T0 of x is equals to 1. If we put n is 1 here in this expression, then we shall have cosine of 1. See that if we put n is 1, we shall have cosine of 1 times cos inverse of x. And this one is the same as writing cosine of cos inverse of x, which is equals to x. Cosine of cos inverse of x, that's a composition of a function and its inverse, which will give us an identity. So we get x. So T1 of x, since T1 of x is equals to x, as we have here. Now for n greater than or equals to 2, we shall substitute theta is equals to cos inverse of x. So what we have here, we shall replace this with theta, so that we can also write, so we replace theta to be cos inverse of x, or even x is equals to cosine of theta. So where we have cos of n times cos inverse of x, when we replace cos inverse of x with theta, then we get cosine of n theta. And now we shall be looking at the expansion of cosine of n theta. And this is where our previous expansion comes in, because we had looked at the expansion of cosine of n theta into powers of cosine of theta. So in this case, we can go back to our previous expansion here, where we had equation 7 here. And we are now saying that Tn of x is equals to cosine of n theta, which means that it can be expanded in this form, in the form that we have here defined by equation 7. While we can use this expression, I want us to just look at another method of expanding that, which is probably much easier than going back to that polynomial, although we can still go and use that expansion. So we are defining Tn of x as a cosine of n theta. So we want to replace n with n plus 1, so that we get t n plus 1 x, which is equals to cosine of n plus 1 theta, like that. And this we can write it as cosine of n theta plus theta, cosine of n theta plus theta. So once we write it in this form, now we can use the compound angle formula in trigonometry to expand cosine of n theta plus theta as cosine of n theta times cosine of theta minus sine of n theta times sine of theta. Now, if we if we now write if we now replace n plus 1 here with n minus 1, so that we write Tn minus 1 of x, then we shall get cosine of n theta times cosine of theta plus sine of n theta times sine of theta. And I want us to add these two expressions. We add these two expressions. So we have Tn plus 1 of x being equals to cosine of theta times cosine of n theta minus sine of theta times sine of n theta, and Tn minus 1 of x is equals to cosine of theta times cosine of n theta plus sine of theta times sine of n theta. If we add these two, then we shall be having Tn plus 1 of x plus Tn minus 1 of x. This is n minus 1 of x is equals to 2 cosine of theta times cosine of n theta. Because now the sign terms will add up to 0. Because one is negative, the other one is positive. Now, notice that cosine of theta, from here, cosine of theta is equals to x, while cosine of n theta from this other expression here is equals to Tn of x. So where we have cosine of theta here, we shall write x. So this becomes 2x. Then cosine of n theta is Tn of x. So in this case, we can transpose this. We want to make Tn, the first term here, we want to make it the subject. So we move the second term to the other side. It becomes negative. And we get Tn plus 1 of x is equals to 2x times Tn of x minus Tn minus 1 of x. So this expression here, we can use it whenever we want to find the Chebyshev polynomials to any value n, given any value n. We can start with n is, we know that we had seen that T0x is equals to 1 and T1x is equals to x. We had obtained that. Remember, we had seen T0x here is equals to 1 and T1 of x is equals to x. So we can consider the case where n is 2. N is 2? We have 0 and 1. So we want to go to T2. So if n plus 1 is 2, then it means that n is 1. So we consider the case where n is equals to 1, so that n plus 1 is equals to 2, and n minus 1 is equals to 1 minus 1, which is 0. So from this relation here, this relationship, we call it the recurrence relation. We shall have T2 is equals to 2x times T1 minus T of 0. So we shall have T2 of x is equals to 2x times T1 1 of x minus t of 0. So, but we have t of 0, t1 is equals to 1. t0 is 1 and t1 is x. So this will give us 2x times x minus t0, which is 1. And this will give us 2x squared minus 1, which is the Chebyshev polynomial of degree 2. Now, if you compare this with the previous expansion, where we were expanding the cosine of theta, the case cosine of n theta, the case where n was 2. The case where n was 2, cosine of 2 theta. You see we have 2x squared minus 1, which is exactly the same expression that we get here. Now, if we want to consider t3, so that we consider the case where n plus 1 is equals to 3, then it means that n is equals to 2 and n minus 1 is equals to 1. So that we write t3 of x is equals to 2x times t2 of x minus t1 of x. From this relationship here, if n plus 1 is 3, then n is 2, and n minus 1 is 1. So we have this expression here. But now we have t2 is 2x squared minus 1. So we can substitute here and write 2x times t2. t2 is 2x squared minus 1. And t1 is x. If we open the brackets, this will give us 4 x raised to power 3 minus 2x minus x. And this will give us 4x cubed minus 3x. And we can now compare this with the case where we had cosine of 3 theta, the expansion of cosine of 3 theta, which was this. And in terms of x, we have 4x cubed minus 3x. And we can see that we're getting exactly the same thing. Now, we can continue expanding like this for n is equals to, we can use now this recurrence relation here. For n is 1, we have obtained 2x squared minus 1. We can go to n is 2, we get that. We can go to n is 3, and we get the expansion, and so on. Now, what is important to note is that the coefficient of the leading term here, can be expressed as 2 raised to power n minus 1. We can always express the coefficient of the leading term as 2 raised to power n minus 1. For example, when n is 3, we have 2 raised to power 2, which is 4. When n is 4, we have 2 raised to power 3, which is 8, and so on. It is also important to note that whenever we are expanding Tn of x, whenever n is odd, then we obtain a series with odd powers of x, like t3 is 4x cubed minus 3x. When n is even, the series contains only the even powers of x. Like t4 is equals to 8x power 4. You see x power 4, x power 2. The constant is just the same as writing x raised to power 0, and we know 0 is an even number. So we have only the even powers whenever n is even. And whenever n is odd, we get only the odd powers of x. So that in this case, Tn of x will be an odd function whenever n is odd, and it will be an even function whenever n is even. Now, we look at a theorem here, which we call theorem 1. The theorem says that the Chebyshev polynomials are orthogonal on the interval -1, 1, with respect to the weight function omega, which is equals to 1 all over the square root of 1 minus x squared. We want to prove this, and we simply want to show that the integral from -1 to 1 of Tn of x times Tm of x divided by the square root of 1 minus x squared dx integrated with respect to x is 0 whenever n and m are natural numbers and n not equals to m. We can also add here that n is non-zero and m is also non-zero. Now, by definition of the Chebyshev polynomial, we write Tn of x is cosine of n times cos inverse of x, and therefore we can replace n here with m and write Tm of x is equals to cosine of cos inverse of x. Then we can substitute in the integral. We can substitute in the integral and write cosine of n cos inverse of x times cosine of m cos inverse of x divided by the square root of 1 minus x squared. We want to replace, we want to set theta to be cos inverse of x, and then x becomes cosine of theta. We want to do that transformation so that where we have cos inverse of x here, we just put theta, here we just put theta, and that becomes the integral of cosine of n theta times cosine of m theta. But we also need to look at the limits of integration. What will be the new limits of integration here when we use that? We see that we are saying x is equals to cosine of theta, so we can differentiate and write dx by d theta is equals to sine of theta, negative sine of theta. And then we can do the transposition here to make dx the subject, sine of theta. We use the identity. We say that sine of theta can also be expressed as the square root of sine squared theta. Why do we need to do this? Because we want to use the identity that cosine of theta squared plus sine of theta squared is equals to 1, so that sine squared theta is equals to 1 minus cos squared theta. And because cosine of theta is equals to x, then we can write this as 1 minus x squared. So we want to use this relation here in our integral so that we replace the sine of theta with 1 minus x squared, but this should be under the square root sign. So we have this. But what about the limits? What about the limits of integration here? Now, let's look at the limits. It's a bit difficult to wrap this. Let me try to do it as much as possible. Yeah, I think that's better. I want to get the limits, the change of the limits of integration. We are using this, or even this one. So we write theta is equals to cos inverse of x. So we can say when x is minus 1, this is the lower limit, theta will be cos inverse of negative 1. And we know that cos inverse of negative 1 is 180 degrees, which is the same as pi radians. So the lower limit will become pi radians. The upper limit is when x is 1, and so theta becomes cos inverse of 1, and we know that cos inverse of 1 is 0. So the upper limits become 0. So the integral will be from pi to 0. So how will the integral look like? So we shall have the integral from pi to 0, cosine of n theta times cosine of m theta divided by the square root of 1 minus x squared. And then dx here is equals to minus the square root of 1 minus x squared d theta. So we substitute that one there. And you see that this quantity here cancels out. And so we are left with the integral of cosine of n theta times cosine of m theta d theta from pi to 0, and there is a negative sign, which is this one. So we can interchange the limits, and then the negatives goes. We change the order of we interchange the limits, the lower and the upper limits, then we do away with the negative. So we have this expression. Now, to work out this integral, we need to use what we call the factor formula. If you can remember from trigonometry, when we write cosine of A plus B is the same as cosine of A times cosine of B minus sine of A times sine of B. And cosine of A minus B is the same as cosine of A times cosine of B plus sine of A times sine of B. If we add these two, we are getting cosine of A plus B plus cosine of A minus B. And if we add the other side, we get 2 cos A cos B. Then the sign term, one is negative, the other one is positive, so those will add up to 0. We want to make this quantity the subject here. So we divide both sides by 2, and we get cosine of A, not plus, it is times cosine of B is equals to 1 over 2 cosine of A plus B, then plus 1 over 2 cosine of A minus B. So we can now replace A with n theta and B with m theta. So that we shall have here cosine of n theta times cosine of m theta. And you see the other side will be a half cosine of n theta plus m theta plus a half cosine of n theta minus m theta. So in this case, we get our next line here. A half cosine of n plus m theta plus a half cosine of n minus m theta. And now, this one we can integrate. the integral, remember, whenever we have the integral of cosine of a theta with respect to theta, we get 1 over a sine of a theta. Of course, plus a constant if it is an indefinite integral. But this one is a definite integral, so we will not need the constant. So we get this. And sine of, remember, n plus m is, n and m are integers. So m plus n is an integer. So whenever we put theta is equals to pi, sine of, whenever we have something like sine of k pi, whenever k is an integer, then we get 0. Also, sine of 0 is also 0. So when we put the upper or the lower limits, we get 0. So the integral is 0. The integral will give us a value of 0. Now we have example 2. We want to prove that the integral of from minus 1 to 1 of Tn of x squared divided by the square root of 1 minus x squared is equals to pi over 2. Now, for this one, we don't have to go back to the basics, although we can just start the same way we started the other one. We replace Tn of x with cos inverse of cosine of n cos inverse of x. That will be the product of that with itself. And we can do the transformation as before, even for the limit. So we shall come to this expression. And again, this quantity will cancel out. And this now will reduce to the integral from 0 to pi cos squared n theta. And now we can use the trigonometry. Remember that whenever we have cos squared x, we write this as 1 over 2 into 1 plus cosine of 2x. This is a trigonometric identity. So when we replace x here with this, with n theta, then we can replace here and we get 1 plus cosine of 2n theta d theta. Then integrate. This will give us a half into theta plus 1 over 2n sine of 2n theta. But sine of 2n theta will be 0 whenever theta is pi, and also 0 whenever theta is 0. So this will give us a half into pi plus 0, and which is pi over 2. That's pi over 2. Now we have theorem 2 that Chebyshev polynomial Tn of x which is of degree n greater than or equals to 1 has simple zeros in the interval minus 1 to 1, and these zeros are of the form xk is equals to cosine of 2k minus 1 over n pi. We can do a proof of this for k. K here will take the values, taking the values from 1, 2, 3 up to n. We can do a proof of this, and we want to let xk, for k being equals to 1, 2, 3, all the way up to n, denote the zeros of the Chebyshev polynomials. The zeros are the values of x that will make this quantity 0. Or sometimes we can just call them the roots of Tn of x is 0. The roots of this equation, or the zeros of the polynomial, means exactly the same thing. So by talking about, by saying that xk denotes a zero of the Chebyshev polynomial, we mean that whenever we replace x with xk, then we get 0. But what is Tn of xk? Tn of xk is cosine of n cos inverse of x from the definition of the Chebyshev polynomial. So we are saying that cosine of n times cos inverse of xk will be 0, meaning that n cos inverse of xk is equals to cosine of 0 is equals to not exactly that. That's not exactly correct. It's cos inverse of 0 cos inverse of 0 or more importantly, this might be a bit confusing. Let me not use that word. We want to write, let's replace this quantity here with theta, so that we write cosine of n theta is equals to 0, where theta in this case is equals to cos inverse of xk. Let's do that one first. So that we have cosine of n theta is equals to 0. Cosine of n theta is 0. And now we can write n theta is equals to cos inverse of 0. But cos inverse of 0, you see that cosine of 0, we know that cosine of 0, we know that cosine of a function, say cosine of a, is equals to 0 when a takes the value of 90 degrees, a value of 270 degrees, a value of value, what other value? At we say we know the cosines. The cosines will be 0 along the vertical axis. So you start from here. Cosine of 0 is 0 at this. This is 90 degrees. Then this one is 270 degrees. So it will be 0 here. Then it will be 0 again here. So 270 plus 180 will be 450, and so on. Then it will be 0 at this point. So cosine of 0, cosine of angles are 0 along the vertical axis. So it is either on the positive side or the negative side. So we are going to use radians. Normally we use radians. So along this we shall be talking of pi over 2. Then here there will be 3 pi over 2. Then the next one will be 5 pi over 2 and 7 pi over 2 and so on. So we have that we have n theta will be a half, which is cos inverse of 0, is a half pi, 3 over 2 pi, 5 over 2 pi, and so on. So that we just need to have an odd power, an odd quantity in the numerator divided by 2. We can write it as 2k minus 1 over 2 pi, for k taking the values from 1, 2, 3, 4, and so on. And now we have saying n theta is equals to 2k minus 1 pi all over 2, so that theta becomes 2k minus 1 pi all over 2n. These are the roots of that equation, but theta is cos inverse of xk. Theta is that, so we are saying cos inverse of xk is equals to 2k minus 1 pi all over 2n. This expression here. And now what is xk? Xk therefore becomes the cosine of 2k minus 1 over 2n pi. K taking the values from 1, 2, 3, and so on up to n. So these are the roots of the Chebyshev polynomial. Now the last theorem that we want to look at here is a theorem that we shall call theorem 3. And this one talks about the relative extrema of the Chebyshev polynomials. The extrema are the minimum and the maximum points, or basically the turning points. What are the turning points of the Chebyshev polynomials? The relative polynomials, the Chebyshev polynomials has the turning points, which we can denote with x bar k, which are equals to cosine of k pi all over n. And this will have the values, the turning points. The value of the turning point will be minus 1 raised to power k. We can do a proof of this, and starting with the definition of the Chebyshev polynomial, Tn of x is cosine of n theta, where theta is cos inverse of x. We can then differentiate this. When we write Tn of x is equals to cos of n theta, and theta is cos inverse of x, or x is equals to cosine of theta. So we can write dx by d theta is equals to minus sine of theta, and the derivative with respect to theta of Tn of x is the derivative with respect to theta of cosine of n theta, and this is minus n sine of n theta. Then we multiply these two. Remember, not multiplication. Remember that the derivative with respect to x of Tn of x, we can now write it as the derivative with respect to theta of Tn of x times the derivative of theta with respect to x. Yes, this is the chain rule. But this quantity, we don't have it. We have the reciprocal of that, dx d theta. So we write this is the same as the derivative with respect to theta of Tn of x divided by dx by d theta. So that we have, this is n sine of n theta divided by sine of theta. When we divide these two, see that the sign will just cancel out. So when we divide, we get n sine of n theta divided by sine of theta. So at the maximum or minimum point, this quantity should be 0. So we equate this to 0, meaning that if this is 0, if this quantity is 0, then it basically means that n sine of n theta is equals to 0, or sine of n theta is 0 because n is non-zero. So n theta is sine inverse of 0. And sine of 0 is usually 0 along the horizontal axis. So it's either here or here. So at 0, pi, 2 pi, 3 pi, and so on. So we have that this quantity here, we can write n theta is equals to 0, pi, 3 pi, 4 pi, and so on, which we can write as k pi. And theta is the same as k pi divided by n. But we know, again, theta is cos inverse of x, so we are saying cos inverse of x bar k is equals to k pi over n. And so what is xk? Xk becomes this quantity here, cosine of x pi, cosine of k pi over n, for k taking the values from 0, 1, 2, 3, all the way up to n. And we can then substitute back xk into the Chebyshev polynomial. And when we do that, we get cosine of k pi, and we know that cosine of k pi will have the value of minus 1 raised to power k. Now, from this result, we can conclude. We see that minus 1 raised to power k can only have two possible values. It can only take the value of 1, positive 1, or negative 1. It will be positive 1 when k is an even integer, and minus 1 when k is an odd integer. So that we can conclude that the maximum value is attained when k is even, and the minimum value is attained when k is an odd number. So basically, that's what we call the Chebyshev polynomials and their expansion. In our next lesson, we shall talk about the monic polynomials and the economization of the Chebyshev polynomials. Thank you.